we move over to Thomas' presentation, and it has a bit to do with benchmarking again, I reckon.
Indeed, it has, yeah.
So you have 20 minutes.
Yes. Perfect. Thanks. So first of all, I would like to thank the organizers for giving me the opportunity to make my talk here, especially given the fact that it's not related to open wallcast in a very direct way. So as you all know, any quantum chemical method always involves a ring of approximations. Like, for example, the most simple case is a basis set, which is always finite, right? And the combined effect of all these approximations is usually difficult to assess, right? So we usually don't have strict mathematical expressions giving us a lower and an upper boundary on our error, right? So we know that we have an error, but we're sort of in that uncomfortable situation that we never really know how large it really is, right? The conceptual implication of all these has actually recently been written about by my boss, and you see that the header of that paper down there. So in any case, we know we have an error. We don't know how large it is. And so what people usually do, and we have just seen that in the preceding talk, is we do benchmarking, right? That's basically the only way we can, the only practical way we have, right? So either we have very accurate experimental reference data or very accurate calculated reference data. And we use that to compare to when we have a method and we want to know how accurate that is. Right? Now, this may maybe a little bit provocative how I phrase it here, especially given the last talk, but I would like to convince you that this approach in certain situations has some shortcomings that we would, or that we should approach in the doc, and we have actually written a paper about that. It's on arXiv and currently in press in PCCP. So the current situation is that, or just a general characteristic in that we always have in chemistry, is that the errors of our quantum chemical methods, whatever method that is, they are distributed heteroscedastically across chemical space. So what we mean by that is they're not distributed evenly, right? So maybe you have a fancy method that produces really good results for a certain class of compounds, but that is no guarantee that it produces the same, accuracy for different molecules, right? So you might be lucky for some molecules, but not so lucky with other molecules. And likewise, maybe you have a method that is very accurate for a certain property, but it's not so accurate for a different property. And so if you have a really small benchmark set, just a handful of molecules really, it's obvious that you are not able to transfer the results of that benchmark to the practical case that you're actually working with, right? So if you have a class just like benzene and some aromatic systems, but I'm actually dealing with some transition metal clusters, nobody would dare to say, if I have an accuracy of 5 kilojoules per mole here, I'm going to have the same error of 5 kilojoules over there with a completely different system. And one way people try to address this is by extending these benchmark sets to make them larger and larger and more general and more general, right? And we have seen in the preceding talk how time consuming and how big of an effort it is to create and maintain such a benchmark set. And so what we wanted to do in that work is we said, well, let's make use of these large benchmark sets. And the example that we chose to work with is that set that was published in 2017 by Markus and Gordon that has about 5,000 data points. We choose that benchmark set simply because the data was easily accessible and in a way in which it was easy to work with. We could have taken any other large benchmark set in principle. The conclusions are general enough to hold for any benchmark set. And so our key idea, what we wanted to do, is to subject this benchmark set to statistical analysis to then understand how conclusions with respect to the accuracy and transferability depend on the composition of that set. So for example, one question you could ask is how strong or how big is actually the influence of a single point in your data set, right? If you have 5,000 data points, you wouldn't necessarily expect that removing a single data point would greatly change your conclusion. And that's actually where we started off, and that's a standard statistical technique called jackknifing. So we have your full benchmark set with about 5,000 data points. You create a second one by just leaving out the first one, okay? And everything else is the same. And then you create yet a new set where you leave away only the second point, and yet another set where you leave away the third one, and so on and so forth. And so you end up with about 5,000 new data sets, every one of which is just one data point more than the original one. So it's a negligible difference, right? And then you can use all these jackknife data sets to basically redo the benchmark, right? And so what Markus and Gordon did there, they basically analyzed density functionals. You could, in principle, use any or replace that by any quantum chemical method. And so here I took that data and I calculated the RMSD of PVE. Why PVE? I just happen to like that function. Qualitatively, the situation always looks the same. The numbers, of course, change slightly, but qualitatively, everything stays the same. And so I have now these 5,000 jackknife data sets, and I calculate the RMSD of PVE, and I assemble these here in a histogram. And so note this is a log scale, so you see that almost everything is happening up here. And this is exactly where the RMSD of PVE, according to the original data set, is. So indeed, we conclude that for almost all sets, or for almost all data points, leaving only them away doesn't really change our conclusions. And that's nice, actually. Right? However, and you can see that marked in that red box, there are a few data points that, when left away, have an unexpectedly large influence on the RMSD. So of course, right, the absolute value is 0.2 keta. That's not large in absolute terms. And also the relative difference there is like 3%. That might not be that much. But still, given that we have 5,000 data points, I just leave away one of them and my result changes by 3%. It starts to be a bit much, right? Also, the entire distribution looks sort of skewed and not too healthy, right? And you can build on this idea of leaving away data points and say, well, what if I not only leave away one data point, but maybe 10? And it actually turns out if you leave away the 10 data points that have the largest error for PVE, you can actually reduce your RMSD by 17%. And now that's striking. And for different density functionals, it's even worse. So for B97MV, I can reduce it by 31% by just leaving away 10 from 5,000 data points. Now, of course, I'm not saying you should not do that, right? I mean, it's not okay if I just arbitrarily go there, take a nice benchmark, and then just throw away all the stuff that makes my method look worse. That's not okay, right? But I claim, but maybe these points could have omitted accidentally. What if I want to create a benchmark set and I'm just not aware of that pooled data over there, just because I'm not aware of it, right? Or maybe the data doesn't even exist because it's a thing that is very difficult to measure and also very difficult to compute, right? Then I just don't have the benchmark data. So what to do, right? And so a first key conclusion that we can draw at this point is that even when you have a really large benchmark set with thousands of points, having a few less or a few more can drastically change how you consider the accuracy of a certain density function in that case, or just by extension, any quantum chemical method. Now one can ask, why actually do a few data points have such a large influence? And for that, of course, the first thing you do is you actually look at these data points. And these are these data points again for PV. It's again a histogram, it's again a log scale. That's the error distribution that we have, okay? And you see again, almost everything plays here. So almost all the errors are below 20 kPa per mole. But there are a few that reach to about 120 kPa and even more. And these exactly, here marked in the red box again, these are exactly the data points. And when you leave these away, you take away a point that has a large error, and that of course brings down then the average error. Now, you're not too surprised when you look at these points that they are so large, because you realize that almost all these points are atomization edges. So these are quantities that grow with system size. And if I get a large molecule, then of course my atomization energy will become large. It's astronomical. And in fact, for this very large error here by about 120 kcal per mole, that's large in absolute terms, I agree. But if you look at how large this error is in relative terms, you realize it's about 0.04%. So in relative terms, that's not so much of an outlier, right? And it's basically okay. The point is just, this figure illustrates that this error that we have is not distributed evenly across chemical space, right? And it covers a wide range. And that's a problem, you know, when I'm interested not so much in what we have seen in the preceding talk, when I have different methods and I want to know how do they compare to each other. But when I'm actually interested in a very specific example, I have a very specific case, some class of compounds or just a single molecule, and I want to know how good is my method there. Then I'm pretty much in the dark when I have such an error span, right? Because I don't know, am I here or am I here? I just don't know, right? And that's a problem. And what I propose, or what we propose here, what you should do in such a case is that you should move away from this traditional, you know, static way of benchmarking and just sort of crossing your finger and hope that you can transfer your results, while in the back of your head, you very well know that you cannot. And you should adopt a system-focused way of doing that. So at that point, I would like to take a step back here and move your attention a little bit to other work that we recently did in our group, and to show like the connections, how that connects to that system-focused way. And you see like a ton of references on there that you can look at if it interests you. So one thing that, of course, sort of immediately gets to your mind is, okay, so given, so just in the hypothetical situation that I now had, such as system-focused benchmarks, it's a set of really accurate data that perfectly matches the systems I'm interested in. I can, of course, use that to just benchmark any method that I want, but I could also go one step further and use that to actually reparameterize my method, maybe my density function, such that it, you know, works even better for the system I'm interested in. And we did that back in 2016 already, and also basically showed how that can be combined with an uncertainty quantification. The idea there being that when you parameterize or reparameterize the density function, you do not end up, or you don't want to end up, with a simple set of parameters for your function, but with a distribution of parameters, such that you can sample from this distribution, basically giving you an ensemble of density functions, right? And for every of these density functions, you can evaluate the property you're interested in, and then you have a set of properties, and the spread of, you know, that set of properties, or the spread of values, can be used as an estimate of the uncertainty. You can ask, well, how do I actually get such a set of parameters? There are different ways to do that. One way that is conceptually rather simple is called bootstrapping. So in bootstrapping, you take your reference data that you now have, and you create sort of new reference data by sampling from it, but with replacement. So if you have a benchmark set or a reference data set with endpoints, you create a new benchmark set that also has endpoints, but because you sample with replacement, it can actually be that in that new set, you have maybe the second point of the old set twice, but maybe another point not at all. So you end up with typically 10,000 of that bootstrap samples. Each one is slightly different from the original, right? And then you can use that to parameterize your model. And because the bootstrap sample is slightly different, the model parameters that result from the parameterization will also be slightly different. And there you have actually a distribution of parameters that you can then use to get basically a spread of the quantity you're interested in. And we showed in reference 5 basically how you can do that in this rather simple case of a linear model for mass power spectroscopy, and we extended that to be able to quantify the uncertainty of D3 dispersion corrections. Now, of course, there's one catch that I didn't tell you about, and this is that it's all good if we, you know, just decide, yeah, we want to do a system for this benchmarking. The problem is just if it were so easy, then everybody here would already do that, right? And the point is, of course, it's very difficult to get this accurate benchmarking. It's time-consuming to measure, or time-consuming to compute. And so what we approach, or what we propose to do, is to adopt like a two-step approach. Only create enough highly accurate reference data that you can train a machine learning model, something like, so we fancy Gaussian processes, but in principle, you could also go for something else, such that you can train such a machine learning model, such that the machine learning model is able for any new compound to specify what the uncertainty is that you have. And now it's important that you use a machine learning model, such as Gaussian process, that also gets you an uncertainty, so that you basically get the uncertainty of your uncertainty, such that you know that when you input a molecule that is too far away from where you parameterize it, that you know that your model is going to fail you. And at that point, you know that you need to create new reference data. And this is a thing that we also already demonstrated in reference set. Right, so in the interest of time, I'm going to skip that slide, and I would like to sum up. So I really think that the fact that the errors of any quantum chemical method are not distributed evenly across chemical space, this is the fundamental challenge when you want to know for a practical case what the error of your method is. Okay? And simply doing a static benchmark and then basically aggregating all the error measures into one final number is going to fail you because it's being too large in some parts of the chemical space and being too small in others. And instead, I propose a simple, or at least in principle, a simple way to overcome that challenge. And this is to do a system-focused benchmark that you combine with a machine learning model to speed it up, that you can then basically retrain whenever necessary. So with that, I would like to thank my boss, Markus Reiher, and all my group members. Financial support by ETH Zurich and the Swiss National Science Foundation is gratefully acknowledged. And last but not least, I would like to thank you for your attention.
So we have time for a few questions. Come on, guys. I have one. So I was naively writing down, how do we measure relevant accuracy? And then I thought, well, maybe I do relative errors. And then, of course, your 100 kilocalories error would disappear and become tiny. But then I might have a measurement of something which is tiny to start off with. Let's say single triplet gap that is 0.1, and my method gets it down to 0.2. Now suddenly it's 200% wrong, or at least 100% wrong. What's the recipe?
Well, I think the recipe really depends on the specific case that you're interested in, right? So the specific property that you're interested in. I mean, one thing that we in our group are heavily engaged with is like just the exploration of very complex and huge chemical reaction networks. And so like one of the primary properties in that case are just the reaction energies. And there, of course, it depends a lot because so say you have two competing reaction pathways and you want to know which one is actually the one that is happening, right? If they're really close to each other and you cannot really decide, is it like that or like that, then your relative accuracy needs to be really, really good. As opposed if you know that the energy is really, the energy gap between these pathways is large, then you can have a much larger relative error in that respect. So I really think that you have to decide on a case-by-case basis what is okay for you. Is it 1 kilojoule per mole? Is it, sometimes you can get away with 10. Right. Sometimes even 1 is too large.
No, it's a similar problem to, usually we use iterative processes, but we use one single threshold, whether it's a system with 2 electrons or it's 10,000 atoms. We're converting it to the same accuracy. And that, to some extent, to me, is not very consistent. And I think that's also go with the errors. All right. Yes.
Yes. So when you look into the outliers of the data set, I mean, now you discussed that one largest outlier, which was just the highest absolute energy. But if you look into other outliers, were there some outliers where you were really surprised?
No. So basically, all these in the red box are exactly at that time. So these are atomizations.
So it's not that there was some small organic molecule that was just behaving very strangely.
It depends what you call small, but no, it's none of these points here in the red box is unexpected in the end. What is a bit unexpected to me maybe is that there are so few of these points, right? I mean, I wonder, is that right that I only have so few points? But the fact that I do have points up here is not surprising to me, and also the fact that it's exactly these points. So if you look at the molecules and the quantities that there are, you do actually expect it.
And, I mean, that's, did you perhaps plot that against divided by the number of electrons or the number of atoms?
I never normalize like the errors to the molecule size. But if you, what you do for these data points, you do have a clear correlation of the not the error, but the underlying value with respect to the molecule size, right? And then if you just say that you have a standard error of 0.04% or something, then of course also this error is increasing with molecule size, which is exactly what we see. So this is like the largest molecule here in that sequence.
One more question there.
So did you ask yourself the opposite question? What happened to those molecules that have a similar size as the one that lead to a high error, but actually don't lead to a high error? So what do you do in those cases? Like why they got it right? Because you're saying that the error went with the size of the system.
Yeah, for some quantities, right? I mean, for these data points about here in the red box, that's just, these are all atomization energies. That's just an extensive quantity that grows with system size. Of course, especially down here, there is a ton of quantities assembled in that benchmark set. Like, it's not like in the preceding talk that we're only dealing with vertical excitation energies or something like that. So here we have everything, also like barrier heights, reaction energies, all sorts of stuff. Like, so we also have intensive quantities which you do not expect to grow with system size. And these are exactly the things that are down there. Okay. Yeah, does that answer your question? I mean, I didn't find a single case where I thought that, you know, depending on the quantity that is measured or calculated, and the molecule size, that the error should actually be larger than it is. So either it was actually a lot. So if it's down here and it's a large molecule, it's an intensive quantity. Or if it's down here and it's an extensive quantity, it's a small molecule. So I basically never found that case that I have an extensive quantity with a large molecule, and I'm not up here or down there.
I have to close now here. If you want to discuss this more during the dinner tonight, you're very welcome. Thank you very much.